Okay, in the next two sections, we're going to talk about volume. And in 6.2, we're going to look at what's called the disk and the washer method. The washer method is really just the disk method used twice, so I suppose that you could just call this section the disk method if you wanted. Some books do that. Let's consider a disk, a circle, of radius r. Okay, then the area of this disk would be pi r squared. Now suppose that we wanted to use several disks stacked together to make a cylinder. Each disk has a radius of r units. Okay, then the volume of a cylinder is where you take the area of the circular base and then multiply by however tall it is. Okay, so I'm just multiplying pi r squared by w. Okay, and that would give me the volume of this cylinder. Now, consider the graph of a curve where the upper half plane is rotated about the x-axis. Okay, each point that is being rotated about the x-axis has a circular path, and the whole graph that sweeps out a certain surface is called a surface of revolution. That's terminology that you'll see in the book. Okay, so as an example, I've got this curve here. And you can think of this as several disks stacked together, just as before, but each disk might have a different radius than the previous disk. Okay? So r of x is a function of x. R of x would also get you the y value at a particular x value here. And I'm rotating this curve about the x-axis, I've shown that, to create this 3D object, let's say, and I want to know the volume of this object. Well, to know the volume of the object, we would need to know the area of each one of these disks and then multiply by the width. So because we are working with a disk at each spot, I'm going to be using pi times the radius squared, just as before, but the radius is a function of x. Okay, so it's still pi r squared, but I'm representing the radius as a function of x, like I said. And then I'm going to multiply that by w, whatever this distance is from A to B. Now, in terms of an integral, okay, we are, pi is a constant that can come out of the integral there. W is really just the distance from A to B here, creating these bounds on my integral. And the integral going from a to b of r of x, the quantity squared, times pi would give me the volume of this 3D object. Okay. Now, I'm introducing what's called the disk method. What I have written here is on the sheet that is also in your notes. I just kind of retyped it all just so it's there for us more to refer to if we need it. So you're welcome to print this sheet if you want. It also has information on it for the next section that we'll look at, which is the cylindrical shell method. 6.3 is the cylindrical shell method. Okay, now with the disk method, it says the volume of the object generated by revolving a function r of x about the line y equal k from a to b is one of these two integral formulas. Okay, now if k is 0, then that means that you're rotating the curve about either the x-axis or the y-axis. In this case, you're rotating about what would be the line y equals 0 or the x-axis. Okay, now anything that is rotated about the x-axis or something parallel to the x-axis, y equal k, is going to mean you'll have an integral set up in terms of x. Be sure that you note that. Okay? Anything that is being revolved about x equals 0, or the y-axis, or x equal k, that is something parallel to the y-axis, means that you'll have an integral set up in terms of y. Okay? So one of the things that I'd like us to do early on is to know the variable of integration, whether it's going to be x or y. That's important. Okay. Now, we're taking the function minus the k value if the volume is below the region that we're rotating, or if the line is below the region that we're rotating, and then we're taking the k value minus the function is squared. Make sure that you're squaring that. If the line is above the region to be rotated. Okay, and so let's maybe take a look at some examples of where we're doing that. Here's an example. Suppose that we want to find the volume of the sphere. Okay, now in a geometry class, you would just be told that, okay, it's v equals 4/3 pi r cubed. All right, now that's nice, but where does that come from? Okay, well, there's lots of different explanations that you can give, but one way to look at it is that you have a semicircle that is being rotated about the x-axis, going to create a sphere. And so you can use calculus. Okay, x squared plus y squared equal r squared is the equation of this circle. So if I solve for y, y would be plus or minus the square root of r squared minus x squared. Now I'm just working with the top half. Okay, I don't want to rotate the top half and the bottom half about the x-axis, otherwise I'm doubling what I've already got there. So it's enough to just simply rotate the top half of the circle, which would be y equal the square root of r squared minus x squared. Now down here, the lower half, which I'm not using, that would be y equal negative the square root of r squared plus x squared, minus x squared. Okay, now I'm rotating this about the line y equals 0, okay, or the x-axis. Therefore, my k value in my setup is going to be 0. Y equals 0 is below the region that I'm rotating. All right, so I'm going to use this first formula here to calculate v. V is equal to pi times the integral. That is going to be something in terms of x. Now the conditions on x is going from negative r to r. Okay, and I'm supposed to take r of x minus 0 squared. Well, r of x would be the function here, this curve, which is the square root of r squared minus x squared. Square that, and okay, that gives us pi times the integral going from negative r to r of r squared minus x squared. You don't need to do it, but if you want to, you can use some symmetry. Okay, like if I find the area under this curve going from 0 to r, and then I double that, then I can get the total area under the curve going from negative r to positive r. Okay. Notice how this curve is symmetric to the y-axis, so that's the only reason why I can use some symmetry here in doubling the area. Again, you don't need to do that, but it's convenient to have a lower bound of 0 rather than negative r. Find the antiderivative. Now this is an integral in terms of x. So r is a constant, right? You're going to have 2 pi times the quantity r squared times x minus 1/3 x cubed. And we're evaluating that from 0 to r. Plug in the bounds now, and you'll have 2 pi times r cubed minus 1/3 r cubed would be 2/3 r cubed times 2 pi would be 4/3 pi r cubed. Okay, well that's the formula that we already know for volume of a sphere. So that's just one way to see where that came from, okay, using calculus. Let's look at some more problems here where we are going to find the volume of the solid that is obtained by rotating the region about the given curve, the region bounded by the given curve about the specified line. Okay. So suppose in this first example we have the curves given by y equal e to the x, y equals 0, x equal negative 3, and x equal 1. I've drawn that region here, that bounded region. Okay, and I want to rotate that region about the x-axis. By the way, for a lot of these problems there might not be a graph there. It's a good idea to draw the picture just so that you can identify, you know, what's the top curve, what's the bottom curve, where you're rotating about. It helps to have a visual, okay? Okay, so here's my picture, and because I'm rotating this about the x-axis, I know right away I'm going to have an integral set up that is in terms of x. So as far as the volume goes, we're going to have v equals pi times an integral. Now the conditions on x are that x is going from -3 to 1. Okay, that'd be the bounds there. And I want to take the function e to the x minus y equals 0 squared. Or that'd be e to the x squared dx. E to the x squared is e to the 2x. And you can use a u substitution if you let u be 2x. du would be 2 dx. A 1/2 would come out of my new integral involving u. Of course, I'll have to change the bounds since my new integral will have to be entirely in terms of u. Right now it's in terms of x. If x is -3, u would be -6. If x is 1, u would be 2. Okay? And antiderivative of e to the u is e to the u. Plug in the bounds, you're going to have pi over 2 times the quantity e squared minus e to the -6. That would be the exact answer. By the way, I mentioned in the last section how all the calculations in 6.1 are going to be positive numbers. Actually, all the calculations that you guys will be doing in the first 3 sections are going to be all positive numbers. Volume can't be negative. Right, so if you ever get a negative, there's a miscalculation somewhere. And probably the first thing that I'd be looking for is the setup. Make sure that you're set up correctly. Okay. Let's take a look at another example. Okay, now a lot of these problems are going to be where you're not going to be rotating about either the x-axis or the y-axis, but you'll be rotating about something that is parallel to one of those two axes. So let's suppose that we want to rotate the region that is bounded by the curves y equal 2 minus x squared and y equal 1 about the line y equal 1. Y equal 2 minus x squared, that'd be a parabola facing down, be shifted up 2 units there, and y equal 1 is a horizontal line. Now, because I'm rotating this curve about something that is parallel to the x-axis, I know right away that my integral setup is going to be in terms of x. Okay, everything about this has to be in terms of x. Now the other thing is that we're not just rotating about the x-axis, but we're rotating about a line that is parallel to the x-axis. The k value here would be 1. Okay, y equal 1 is below the region that you see I've got shaded there, the bounded region. Now, I've got all these formulas written on a sheet. Quite honestly, I really don't think that we need to have formulas memorized. Okay, one of the things that I want to emphasize on when you're setting this up is remember what we have already talked about in 6.1 with area between two curves. Okay, I'm taking this area between two curves. Well, how do I find that? Take the top curve minus the bottom curve, right? And that's exactly what I'm doing. I'm taking the top curve, which is 2 minus x squared, minus the bottom curve is 1. Right? I don't need a formula for that. I'm supposed to square the integrand. And since this integral is all about x, I know x is going from -1 to 1. All right? And so here'd be my setup. Now make sure that you square the integrand. That's a mistake I'll see students sometimes forget about. There is they forget to square the expression. All right, so now I'm all set up. Now it's just a matter of finding this number here, and of course it's going to be a positive number. Okay, and so let's get at it. 2 minus 1 is 1. 1 minus x squared times 1 minus x squared. That'd be 1 minus 2x squared plus x to the 4th. And the antiderivative then would be x minus 2/3 x cubed plus 1/5 x to the 5th times pi, and then we're evaluating that from -1 to 1. Plug in the bounds. When you plug in 1, you're going to have, let's see, pi times this whole thing. 1 minus 2/3 plus 1/5, and then minus, when I plug in -1, it's going to be -1 plus 2/3 minus 1/5. Okay, and when you simplify all this, you should be getting 16 pi over 15. and make sure that it's in exact form, and of course simplified form. Okay, that would be the exact volume of this 3D object. Kind of looks like a football or something like that. Okay, 16 pi over 15 cubic units would be the volume of that 3D solid. Okay, now on the sheet here in the top half, so up here I'm talking about revolving a function about you know the y-axis, or excuse me, the x-axis, or something that is parallel to the x-axis, like a y equal 1 or y equal whatever. So how about, what if we're rotating about the y-axis, okay, or something that is parallel to the y-axis, like x equal 2 or x equal -3 or something like that. Okay, well, your integral is going to be in terms of y now. Okay, and you're going to use this form if x equal k is to the left of the region to be rotated, and you'll use this form if x equal k is to the right of the region to be rotated. Again, I don't think we need to know formulas here. Okay, they're there for you. Okay, but remember what we have already talked about: right curve minus left curve. That's all I'm doing. Okay, when I set up the inside part here and I square it. So let's take a look at some examples. Suppose that we have the curves y equal x squared, y equal 4, x equals 0, and I want to rotate that bounded region about the y-axis. Okay. Now, because I'm rotating about this region about the y-axis, I know right away that I'm going to have an integral set up in terms of y. Probably the mistake that I'll see the most in something like this is that a student won't get the correct variable of integration. They'll be doing stuff with x when it should be y, or they'll be doing stuff with y where it should be x. So that's why I said, early on, identify the variable of integration. That's key in this. Now the conditions on y, I've drawn that picture of this bounded region that we're describing. The conditions on y is going from 0 to 4, and I want the right curve minus the left curve. Now y equal x squared is the right curve, but I need everything to be about y here when I get this set up. So if y equal x squared, x would be equal to plus or minus the square root of y. Okay, x equal the square root of y would be the right half of the parabola. X equal negative the square root of y would be the left half. So because I'm working with just the right half, I just need the square root of y. And then minus the k value would be 0. So I'm looking at root y minus 0, the quantity squared. Again, right curve minus left curve. That's it. And of course, stick a dy there. When you integrate y dy, you're going to have 1 half y squared. Of course, make sure that pi is there. We're evaluating this from 0 to 4, plug in the bounds. 4 squared is 16, half of 16 is 8. 8 pi minus 0 is 8 pi. That'd be the answer there, the volume of this object. Okay, let's maybe do one more. Suppose that we have y equal 1 over x, y equal 1, y equal 3, and x equal 2. I've drawn that region there, that bounded region, and we're going to rotate that about x equal 2. Now, because I'm rotating this region about a line that is parallel to the y-axis, I know right away I'm going to set up an integral where everything is going to be about y. Okay. The conditions on y in this problem, y is going from 1 to 3. Okay, so that's going to be my bounds. Inside the integral, I want the right curve minus the left curve. The right curve is x equal 2. The left curve is y equal 1 over x. Now, I don't want 1 over x, right, because everything has to be about y here. If y equal 1 over x, then that means that x equal 1 over y. So the left curve would be 1 over y. Square that. Make sure there's dy there at the end. And we're all set up, and now I can begin to calculate this number here. So we'll have pi times the integral going from 1 to 3. I'm foiling this out on the next line. And then I'm ready to take the antiderivative here. It's going to be 4y minus 4 times ln of the absolute value of y. And then minus, so the antiderivative of y to the negative second would be y to the negative first divided by negative 1, or that'd be a minus 1 over y. We're evaluating this from 1 to 3. Plug in the bounds, and of course don't forget about pi. There should be pi there, sorry about that. So we've got pi times the quantity, 12 minus 4 ln 3 minus 1/3, and then minus, when you plug in 1, it's going to be 4 minus ln 1 is 0, and then minus 1. Okay, when you simplify what's inside the brackets there, I'm getting pi times the quantity 26/3 minus 4 ln 3. If you were to check that, that would be a positive number in a decimal form there. Okay, but again, we'll just keep our answers in exact form here is fine. So that's the disk method. Now, the washer method is also in this section. It's really just the disk method used twice. I'll talk about that in the next video, though.